This movie is a review of two important blood gases, oxygen and carbon dioxide. Oxygen is required by your cells for cellular respiration to make energy, and carbon dioxide is a metabolic product of cellular respiration. So we'll spend a little time looking at these blood gases and what drives the movement of oxygen from the air that you breathe into your blood so it can be delivered to your cells, and also how carbon dioxide that's generated by cells in your body and and then moves into the blood, how your body can work to blow that off, to actually remove the carbon dioxide from the blood to get it to move from the blood into the air, right? So that you can expire it. So first, some basic background. So a gas is a state of matter wherein the particles have no regular arrangement and move freely at high speeds, which is unlike what you would find in a liquid and certainly a solid. And there's one gas, or really mixture of gases, that we're all, I think, really familiar with, and that's the air that we breathe. So we can take a step back here and think about the air that we breathe and also draw on some concepts of pressures of gases and what really drives the movement of one gas from one place to another, or for instance, from the air into your blood. And I think that'll make a little more sense coming up. But let's say, for example, that you are sitting on a beach, so you're at sea level. That means your elevation is 0, and there's a specific defined volume of air then that exists above you, between you and space. That amount of air applies a pressure to you. So there's a pressure that you experience. It's 1 atmospheric pressure. It's also 760 millimeters mercury. But of course, the air that we breathe is it's a mixture of gases, and the major ones are nitrogen, oxygen, argon, and then some other gases exist too at a lesser concentration, for instance, carbon dioxide. And the percents that make up this mixture of gases are roughly 78.1% nitrogen, roughly 21% oxygen, about a percent argon, and then again there's some other less abundant gases, one of which is carbon dioxide, which is about 0.04% of the total gases in the mixture. And this is the same, these percents are the same whether you're at sea level or if you're on top of Mount Everest. It doesn't matter, the percents are the same. But what will be different depending on where you are or what your elevation is the amount of pressure that they contribute. So let's take a look at a specific example here. So at sea level, the pressure is 760 millimeters mercury from all of these gases combined. But because nitrogen, for instance, is only 78.09%, it doesn't contribute all of that pressure. It just contributes 78.09% of that pressure. So we can simply multiply 760 millimeters mercury by 0.7809, and that'll give us the partial pressure, 594 millimeters mercury, that just nitrogen, that single gas, is contributing from or of the total pressure. And it's relatively straightforward to look at all the other gases too. You just multiply 760 millimeters mercury by their different percents to get what their specific partial pressures are. And we care about that because when we think about partial pressures, that's really what's driving the movement of a gas from one place to another, or again, for instance, from the atmosphere into your blood, or from your blood into the atmosphere. Gases will move from a high partial pressure to a relatively low partial pressure. Okay, and they'll continue to do so until those pressures are equivalent, until they've equilibrated. So we can look at what we really care about here in terms of the movement of gases between the atmosphere and your blood are these microscopic structures here, the alveoli. So they look a little bit like bunches of grapes. And this, when you breathe, is what you're drawing air from the atmosphere into these alveoli. And you're bringing them into close proximity to capillary beds that surround the alveoli. And blood is brought into the lungs via the pulmonary arteries and leaves via the pulmonary veins, shown here. So it's within these alveoli that carbon dioxide and oxygen move between the blood and the air. And generally, oxygen moves from the air that we breathe into the blood, shown here in orange, and carbon dioxide, shown here in yellow, moves from the blood into the air spaces within the alveoli so that you can expire the carbon dioxide. So what's driving the movement of gases from one place to another? Again, it's at partial pressures, so we can look at specific examples here. So the partial pressure of oxygen coming from your body, from the systemic circuit and then into the pulmonary circuit towards your lungs, is oxygen poor, relatively, because the oxygen here has already been depleted or used up to some extent by the tissues in your body. So how can you move oxygen into the blood? Well, you see here that it's 40 millimeters mercury in the blood that approaches an alveolus or is coming towards the lungs. And within the airspace of the alveolus, the partial pressure of oxygen is about 104 millimeters mercury. So it's going to move from where it's high to low. It'll move from 104, where it's high, into the blood, where it's relatively low, at 40 millimeters mercury. And it'll continue to move until an equilibrium has been met, and the partial pressure of the blood is 104 millimeters mercury, leaving the lungs. As it turns out, there's a little bit of mixing within the systemic circuit supply of the lungs, and also what's leaving the lungs here through the pulmonary veins. So by the time the blood reaches the left side of the heart, left atrium, left ventricle, and out towards the systemic circuit, the oxygen's been mixed a little bit with oxygen poor depleted blood. So ultimately what actually reaches your body tissues is really more like 95 millimeters mercury. Okay, so now we have a partial pressure of oxygen at 95 millimeters mercury, and it's going to approach through capillary beds cells within your body tissues. And your body tissues that have been working hard to metabolize and using oxygen to make energy exist at around 40 millimeters mercury oxygen, partial pressure of oxygen. So again, the partial pressure of oxygen is relatively high in the blood here, 95 millimeters mercury, relatively low in your body tissues at 40 millimeters mercury. So it'll move from the blood into your body tissues until it's equilibrated. Okay? And what's left behind is going to be oxygen poor blood because the oxygen's moved into the body tissues. So it's equilibrated at about 40 millimeters mercury, and that is what's going to make its way back to the right side of your heart, right, through the systemic circuit, and then into the pulmonary circuit, which is where we're back to where we began at 40 millimeters mercury. So carbon dioxide, we'll think about that now. With the blood that's approaching an alveolus, it's about 45 millimeters mercury. And the air within an alveolus is a little bit lower, at 40 millimeters mercury. And again, remember what the object here is to get carbon dioxide out of the blood. Right? It's to expire or blow off the carbon dioxide, which is perfect because if you look at those partial pressures, it's going to move from high to low. So the carbon dioxide will diffuse out of the blood, where it's relatively high at 45 millimeters mercury, to where it's relatively low at 40 millimeters mercury. And it'll continue to do so until it equilibrates at 40 millimeters mercury. So that blood will make its way back to the left side of the heart, out towards your body tissues, where this blood at 40 millimeters mercury will encounter body tissues that have been busy metabolizing, busy creating carbon dioxide, and the partial pressure in the body tissues is going to be roughly 45 millimeters mercury, okay, which is relatively high. So it's going to move from where it's high in your body tissues towards where it's low, which is the blood, okay, until it reaches an equilibrium, and the carbon dioxide leaving your body tissues is going to have a partial pressure of 45 millimeters mercury. Again, that brings us back to the beginning of the story of 45 millimeters mercury of the partial pressure of carbon dioxide approaching or coming towards the lungs. Okay, so the blood transports, as we've seen, oxygen and carbon dioxide between the lungs and the body cells. So these gases, how are they going to kind of be transported or move around within the blood? Some of it is just diffused in the plasma, so it's the gas moves into the liquid part of the blood and exists there within that fluid. But some of these molecules also combine with other substances. Some of the gases also combine with other substances. So with oxygen, there's two methods of oxygen transport in the blood. And the first one we've encountered quite a few times. This is hemoglobin. Okay, 98% of oxygen carried in the blood is bound to hemoglobin, and hemoglobin is a protein. It's shown here on the left. It has 4 subunits, 2 shown here in blue, 2 in tan or gold. And at the heart of each subunit is what's called a heme group, and the heme group is bound to iron or contains iron. And it's that the oxygen actually binds to. So oxygen can bind to the core of each of these 4 subunits. Okay, 98% of the oxygen carried in the blood is bound to hemoglobin. Okay, and hemoglobin is that protein that is packed within the red blood cells shown on the right and actually gives those cells their color. Then the other 2% is simply dissolved in the plasma. So hemoglobin is actually a really interesting protein, and we can look at the way that it binds oxygen, and we can kind of map out its affinity for oxygen, or in any particular context, how much of the hemoglobin protein is bound to or saturated with oxygen. And not surprisingly, it's actually dependent on the partial pressure of oxygen. Or to put it another way, if there's more oxygen, the partial pressure is higher, then more of that is going to be bound to hemoglobin. So if you look at the bottom axis here, the x-axis, you can look at the partial pressure of oxygen. Again, those values are increasing. And as they increase, shown here with this S-shaped, sigmoidal kind of shaped curve, as the partial pressure increases, the amount of hemoglobin that's saturated with oxygen also increases. So we can look at one value here, which is relatively low. 26.8 millimeters mercury is the partial pressure of oxygen. At that partial pressure, 50% of the hemoglobin is bound to or saturated with oxygen. Okay. And if there's more oxygen, so let's say an 80 millimeter mercury partial pressure of oxygen, probably not surprisingly, you'll find that more of the hemoglobin is bound to that oxygen. Okay, roughly 96% or so of the hemoglobin is bound to oxygen when the partial pressure of oxygen is 80 millimeters mercury. There are some factors that impact how much of the hemoglobin is bound to oxygen, and this, as it turns out, is really interesting because they're tied to what you might expect. If a tissue in your body is really metabolically active, it's going to be depleting oxygen, so oxygen levels in that little micro area will be relatively low. It's going to be generating a lot of carbon dioxide because there's a lot of metabolism going on to make carbon dioxide. As a result of increased carbon dioxide, the blood is going to become a little more acidic, so there's going to be a change in pH. And also temperature is going to be higher in a metabolically really highly active area. And as it turns out, the concentration of oxygen, carbon dioxide, the pH or acidity, as well as the temperature all impact how tightly hemoglobin binds to oxygen. In a metabolically active tissue, okay, with high carbon dioxide, relatively acidic, and high temperature, the hemoglobin binds to oxygen less tightly because the expectation is that the tissue is going to need that oxygen. it wouldn't be beneficial to have the oxygen tightly bound to hemoglobin. So let's take a little more detailed look at this. So factors that are going to increase the release of oxygen from hemoglobin would be a decrease in the partial pressure of oxygen. So when oxygen levels are low, the partial pressure is low, you might expect that the tissue needs oxygen. So hemoglobin more readily kind of relinquishes it or gives it up. Also an increase in the partial pressure of carbon dioxide, which would be a direct result of a really metabolically active tissue, is going to promote the hemoglobin in the blood there to more readily increase its release of oxygen, right? Because the expectation is that the tissue is going to need it. And acidity is directly related to the partial pressure of carbon dioxide. So if there's more carbon dioxide in an aqueous solution, it's going to become more acidic, and that also impacts how tightly hemoglobin binds to oxygen. And lastly, an increase in temperature. So an increase in temperature you might expect if a tissue were very active. And if a tissue is very active, it's probably going to need oxygen. So the hemoglobin increases its release of oxygen. And we can look specifically at one example here. So let's just look at the acidity or the pH of a solution, specifically of blood that hemoglobin exists in. And we can see on the bottom here, there's a partial pressure, and let's just pick a value. Let's say 45 millimeters mercury. If we follow that line up, and let's start with a pH of 7.4, we can see how much of the hemoglobin is saturated or bound to oxygen. Okay, it's roughly 80%. But now imagine a more acidic environment, because a tissue is metabolically very active and it's producing a lot of carbon dioxide, okay, which is going to drop the pH and make it more acidic. So let's say a pH of 7.2. In this context, only 68% of the hemoglobin is saturated with oxygen, or to put it another way, the hemoglobin is more readily giving up the oxygen, again because the expectation is that these metabolically active tissues are going to require the oxygen. So it's a really interesting, beautiful biological mechanism whereby hemoglobin alters its affinity for oxygen depending on the needs and the context. So how is carbon dioxide transported through the blood? There's really three methods. And the first one is really direct. About 7% of the carbon dioxide is simply dissolved in the blood plasma. So it can make its way out of the body tissues, diffuse into the blood, dissolved in the fluid portion of the blood, and make its way back to the lungs that way. 15 to 25% of it is bound to hemoglobin. So we usually think about hemoglobin as being a protein that binds to oxygen. Well, that's true, but it also binds to carbon dioxide. And when hemoglobin is bound to carbon dioxide, it's called carbaminohemoglobin. So about 15 to 25% of the carbon dioxide kind of hitches a ride on hemoglobin to make its way back to the lungs. The majority of carbon dioxide is transported as part of a bicarbonate ion. So what does that mean? Well, bicarbonate ions form as a result of a reaction between carbon dioxide and water. So carbon dioxide and water together can react and they'll form carbonic acid, shown here, H2CO3. So this is an acid. And this doesn't happen very quickly in blood plasma, but there's actually an enzyme present in red blood cells called carbonic anhydrase that catalyzes this reaction. So the carbon dioxide makes its way from body tissues into the blood, then makes its way from the blood into red blood cells. Okay, and there the reaction with water is catalyzed to form carbonic acid. And once you have carbonic acid, this pretty quickly ionizes into what's shown here as a hydrogen ion and a bicarbonate ion. And it's in this form that carbon dioxide is integrated into this bicarbonate ion to make its way back to the lungs. As it turns out, fortunately, this reaction is reversible, so that as the bicarbonate ions and as the hydrogen ions make their way in the blood back towards the lungs, they can then again form carbonic acid, shown here in the middle, H2CO3. So now we're moving right to left. And then the carbonic acid can break down into carbon dioxide and water in the blood in the lungs, and then diffuse from the blood into the air spaces in the alveoli, and then you can expire the carbon dioxide that way. So this has been a quick review of two really important blood gases, oxygen and carbon dioxide, as well as what drives their movement between the air spaces in the alveoli and your blood.